Hi, I'm happy to talk to you tonight about complex numbers. I hope you're excited about this lesson as much as I am. As a review, let's talk about imaginary numbers. Remember that an imaginary number is just a non-real number created by taking the even root of a negative number. For example, the square root of negative 16 would produce is an imaginary number. Now the reason is, well, we don't have a number that multiplies by itself in the real world that would ever equal a negative number, right? So in our real number system, it's impossible to get a negative inside the radical, right? Now what we did is we said, well, the square root of negative 16 is the same thing as the square root of negative 1 times 16. And what we said is, by definition, the square root of negative 1 is the letter I. So if you see a negative inside a radical, you just bring it out and make it into an I. You don't actually have to break this down into negative 1 times 16. And then the square root of 16 is just 4. So the final answer to this of square root of negative 16 is 4i. So what that means is that if I square root a negative, or fourth root for that matter, I always produce an imaginary value, something that's not part of the real number system. Now remember, earlier in the year, we talked about the real number systems as being things like natural numbers, whole numbers, integers, rational numbers, and irrational numbers. So inside the real number system, we had numbers like, well, 5. I can count to 5. And we had numbers like the square root of 7. And I had some like 2/3, or 0, or negative 9. Right? These are real numbers, right? Well, now we have a system of imaginary numbers, right? Imaginary numbers will be numbers that are created by square rooting negative values, like, again, the square root of negative 16, or the square root of negative 5, or the square root of, say, negative 12, okay? Which we talked about again last week. You can also have things like the fourth root, and that's why we write the fourth root of negative, say, 8. And we'll talk more about that kind of imaginary value later on this year, okay? So now I have two separate systems of numbers. I've got the real number systems on my left, and I've got the imaginary numbers on my right. Well, if I were to take this number system and merge them together, what I would get is something called the complex number system, right? And a complex number system is one where you have all the numbers that are real over here, the imaginaries over here, but you could also have numbers in the middle that are a little bit imaginary and a little bit real. And we call those complex numbers in the form a plus bi, where we say that a is the real component or the real part, and bi is my imaginary component or part. So if I have a number like, say, 3 minus 5i, this is a complex number with a real component of 3 and an imaginary component of negative 5i. Okay? Now, altogether, we call a plus bi standard form of a complex number. Okay, so if you take a look at this, I basically have three regions for the complex number system. I have the numbers on the left, we call these the pure real numbers. I have numbers in the right region, these are pure imaginary numbers. And then I have this center region right here. This center region right in here is a mixture of both real and imaginary, right? So, if I saw the number just say 8, well, that's a complex number. It has a real component of 8 and an imaginary component of nothing, so 0i, right? So even if I have a real number, like what we're used to seeing in the old days, like a number 8, well, that's a complex number with a real component of 8 and an imaginary component of 0i. Similarly, if I have, say, again, the square root of, say, negative 12, well, I know that simplifies to 2i root 3, right? Well, in this case, I have an imaginary part, but I have no real part. So this is a pure imaginary with 0 as its real component, okay? The next thing we want to do is take a look at how we plot our numbers that are complex. Now, as a review, take a look at a real number, right? We know that real numbers, back in the day, back in 2nd, 3rd grade, whenever you started learning about numbers, that we plotted our numbers on a real number line, right? Where this is the real axis right here. So if I had, say, the number 3, well, what I would do is I would go over to the right 3 and put a little dot, okay? If I had the number, say, negative 1.5, I would come over to negative 1.5 and put a dot, right? We get this, right? Well, similarly, I need to be able to plot an imaginary number, right? Well, if I have an imaginary number line, we'll make this right here. If I knew how to spell imaginary. Right? Well, if I have 3i, well, again, I'll put a little dot right there. Right? And if I had, say, negative 1.5i, not that we like to mix decimals very often with i's, but it would be like right there, right? And so notice that in the imaginary number system, you graph them just like you would at a real number, right? Notice, I do not need to put the units for I. I don't need to put I there. We've defined this to be the imaginary number line. I don't need to write i's next to each one of these. Now, that's if you want to graph or plot pure reals, right? Or pure imaginaries, like this, right? Well, what if I wanted to plot a complex number that had both a real component and an imaginary component? How would that look? Well, our plan is to take the two number lines and merge them into one. But the problem is, since they're both horizontal at this point, that would be confusing. So what we do is we take the imaginary number line, we turn it vertical, and we cross it with the real number line. And what we get is a system that looks very similar to an XY plane, where the imaginary axis is the y-axis and the real axis is your x-axis. So if I wanted to plot a point or a number that's a complex number, say for example, negative 3 plus 4i, all I would do is imagine an xy plane. But instead of calling my x-axis x, I would call it the real axis. And instead of calling my vertical axis the y-axis, I'll rename that with the imaginary axis. So we call this the imaginary axis, and this then the real axis. So if I want to plot negative 3 plus 4i on a number line, or on the imaginary and real axis, that tells me to go negative 3 along the x or real axis and 4 units up along the imaginary axis until I get to this point right here. And this point is negative 3 plus 4i. Okay? Again, let's try it one more time. Suppose I wanted to graph just 3 minus 2i. Again, what that would tell me to do is I'm going to go along the real axis 3 units. Let's try this again. So from the origin, go 3 units to the right and down 2 units on the imaginary axis. And this point right here is the point 2 minus 3i. Okay? right, now, let's go back to the very beginning of our discussion of real numbers, right? Now, with the real number system, if I have a number like, say, -4, and I want to find its distance from its position on the number line to 0, remember that we call that the absolute value. And we use these little absolute value sticks to represent that. But remember that the absolute value just talks about the distance the number is from 0. And in this case, it's 4 units, right? Well, what happens with a complex number? If I want to find the distance from, say, -3 plus 4i back to 0, wouldn't I be looking for the length of this green segment here? This is what I'm looking for. Well, at this point, we're going to have to call on an old friend from geometry to help us find that length. As you recall, our oldest friend in geometry and most trusted friend in geometry, well, if you don't remember, or maybe you never met this friend, but I'm pretty sure you did.
Hello?
Mr. Cohen, how are you?
Wonderful, Mr. Kong. How is everything?
I'm doing well, I'm doing well. Listen, I'm putting together a screencast for kids on complex numbers, and at this point we're trying to find the absolute value or the distance that number is from 0, or shall we say the origin. Can you remember what we used to find, what tool we could use to find that absolute value?
I think it's the Pythagorean theorem.
Well, golly, thanks, Mr. Cohen. What would the two sides of my right triangle be?
A and B.
A and B, where A is the real component and B is the imaginary component?
Yes, sir.
Thanks for that Pythagorean theorem. I appreciate that, Mr. Cohen. We'll see you in school.
Take care.
Bye-bye.
Bye.
Alrighty, so Mr. Cohen says that I could just use the Pythagorean theorem. If you look at this, I have a right triangle formed on this plane, where the horizontal side is 3 units long, and the vertical side is 4 units long. Now notice, again, I don't care about the number, whether it's negative or positive, I just care about the length. Well, again, to find that value, couldn't I go c squared equals a squared plus b squared? So c squared equals 16 plus 9, or c squared equals 25, and so lo and behold, the length or the distance, the absolute value from this number back to the origin is 5 units. So we say the absolute value of -3 plus 4i is 5 units. What do you think the distance from 2 minus 3i back to the origin would be? How far do you think that would be? I'll give you a second to think about that. Well, let's see. Again, if you got this to be 3, and this is 2 units long, again, I don't care about the I and I don't care about the negative. I just draw a right triangle out. We'll see. 3 squared is 9, plus 2 squared is 13, so this distance is the square root of 13. So we say that the absolute value of 2 minus 3i is the square root of 13 units. Now, hopefully, what some of you are figuring out is, if I have a complex number, a plus bi, if I want to take the absolute value of that number, again, the positive and negatives doesn't matter because, again, the a and the b represents how long you're going to count on each axis, right? The a is for the real length and the b is for the imaginary length. But if you think about it on the axes, isn't the real side just going to be the horizontal leg of the right triangle? And isn't the imaginary axis just going to be the vertical leg of the right triangle? And so wouldn't the distance be the hypotenuse? And so couldn't you say that the absolute value of a plus bi is just equal to a squared plus b squared? Well, that would be the hypotenuse squared, but if you square root that, then that would be the absolute value. So if you don't want to go through graphing out that point, plotting out that point every time, and then drawing your right triangle, you could use this. So as an example, if I say, find the absolute value of negative 5 minus, say, 12i, what would that distance to the origin, or what would the absolute value be? Try that on your own. Pause me. I think you should get the square root of, let's see, negative 5 squared. Oh, I don't care about the negative. That's right. So don't ever put negatives in there. So just 5 squared plus 12 squared, because I don't care about the positive or the negative. Notice I also don't put the I. Wouldn't that just be 25 plus 144, which is the square root of 169? So I say that the absolute value of negative 5 minus 12i is 13 units. And I've just found the absolute value. Again, could you plot it out each time, just a sketch, and then draw your right triangle to do Pythagorean theorem? Yeah, but this little formula right here can also be used, okay? All right, now let's shift gears.